Hey guys, so I've read some of the comments on the previous video, the I'm back one, and I was very happy to see that some people actually missed me, and I really appreciate that. And here's hoping to, I'll see you more often, or actually, you're gonna see me more often. Today I have a different thing. Um, I told you that I got a lot of new test equipment and stuff like that. One of those things I have on loan from a very dear friend. He's an avid collector of everything, everything electronic, and he lent me some of his Tektronix plugins, one of which is the venerable 7CT1N. It's a curve tracer plugin for 7000 series oscilloscopes, and it's actually a very competent instrument for general purpose lab use. So you can check transistors, bipolars, MOSFETs, JFETs, diodes, and other semiconductors. And not only semiconductors, you can also check resistors and stuff like that. And it's very, very cool because it's an entirely analog device. It's completely analog. There's no logic, no digital logic inside it. And it's very, very interesting as an exercise of design. So design brilliance by whoever designed it at Tektronix. So I have the schematic for it. I hope you can see well enough. This is the whole thing, the whole curve tracer. And I was going to go through the schematic a bit and show you a bit of the building blocks and explain some of the design choices they went to, and kind of show you the operation of the thing a bit later in the video. So what does a curve tracer do? Well, it basically it sweeps the collector voltage or the drain voltage of a semiconductor while applying various base or gate biases, so you can get the output characteristics of a transistor. That's basically what it is. It just plots the characteristic curves of a semiconductor. You can even use it to plot the characteristic curves of some lower voltage vacuum tube devices as well. But other curve tracers with higher collector voltages are more suited for this purpose. So I'm just going to zoom in a bit here when I'll take a look at the schematic and some of the building blocks. So this is a triangle wave oscillator. It's made out of an op-amp and a couple of transistors. This is a hysteresis comparator. So a comparator that has some hysteresis. And this point here will have a triangle wave that kind of looks like this with a tiny gap in between. And this is basically the start of the circuit. This gets amplified. This is a classic Class B amplifier. Was used for audio amps for quite a long time. And it's got some non-inverting gain. It's got global feedback. So R33 and R22 actually form the gain of this amplifier here. Theoretically, it's R21 and 22 in series with this. So because you bring the feedback from the output of the amplifier to its input, this is a closed loop amplifier, and it's got much better frequency response and flatness and stuff like that than an open loop amplifier. This drives a transformer, which is inside the curve tracer. It's actually quite nice. And you have some settings here that are available on the front panel of the instrument. And these settings basically tap off different taps of the transformer in order to get different collector voltage sweeps. There's a bridge rectifier because for this instrument, we're only interested in one polarity. So the collector voltage always goes positive. And then yeah, you can see there's no filtering. That's because we want to have a sweep. So if you want a DC here, There is a mode that's used to test leakage currents of devices, and it actually filters the output so you don't get a sweeping characteristic curve of the semiconductor. You just get a bias point that you can move across. Then you have a difference amplifier with a couple of source followers. These are high impedance devices. These are JFETs. And the difference amplifier that basically measures the voltage across the collector emitter of the transistor. And this goes basically to the output. The output is actually a terminal that it's a BNC cable that you have to yank out of the instrument and plug it into a vertical amplifier in the Tektronix. For the emitter current or the source current, there's a bank of resistors here, which are actually shunts, and they're configured by these switches, and an amplifier that basically senses the voltage across these resistors, and that gives you the collector current or the emitter current basically. Now, some of the interesting aspects of this device here are there's no logic responsible for generating the step pulses. So for every sweep of the collector, there will be on this point here basically a voltage or a current step that kind of looks like this. And how would you go about doing that without a counter or some DACs or some stuff like that? Because remember, this is a 1970s device. It wasn't a full-fledged curve tracer, so unlike the 576, which has a counter and some logic and stuff in there, this doesn't have the benefit of using very expensive parts. You can see that instead of using another LM741 in here, they used like 4 transistors and some passives. Well, this is Tektronix's design brilliance. So every zero crossing, this is a zero crossing comparator, every zero crossing, this circuit here generates a bunch of charge, like a quanta of charge that is yanked out of this integrator here. This is an integrator. You can see there's a capacitor in the feedback. And every zero crossing, so you don't get distortions in the trace and stuff like that, you get a voltage on the output that jumps up by a step. The amount of voltage that it jumps by per step is kind of fixed, but you can calibrate it internally. There's a trimmer inside that you can do that. So a comparator, both of the collectors are sensed and ORed through diodes. They turn on this transistor every zero crossing, which pulls the this node low every zero crossing and pulls some charge out of this integrator. This charge is always the same because it's basically the amount of charge that was stored on this capacitor here. So you can see that's a 22 nanofarad and the integrator capacitor is 100 nanofarad. When you've reached the preset level of steps, so the number of steps that you want to draw the characteristic curve for, there is a comparator here that samples the output, and this circuit is sort of like a one-shot. So Q104 gets driven, it conducts, it pulls the base of Q108, which is a PNP, down, which makes it conduct, which hits a small pulse of current through C108, which is 470 picofarads. It turns it off, and that pulse also goes through CR111, the capacitor and this resistor, and turns this thing on briefly. And you can see it's across this capacitor basically, and it just resets the integration capacitor, so it brings it back down to 0. Apart from that, you can have a constant voltage offset that you apply to the step generator, and this is very simple. It's just a voltage source. It's made out of 2 transistors, and it's enabled by this pull switch. And yeah, this is just a brilliant schematic. You can also have current fed into a base of a bipolar, or just voltage fed if you're looking at a JFET or a MOSFET or something like that. I love the way that Tektronix draws their cam switches. Every dot means a closed contact, and you can see that basically these are the positions on a rotary switch, and every dot means close contacts for all of these. Yeah, so basically this is the entire schematic of the thing, as I've said. Another interesting aspect is that the comparator reset as well as the step all take place when the collector voltage is at 0. That's very important because otherwise you'd have a very erratic looking display. And all of this is just a masterclass in analog electronics design. It's really, really beautiful. Everything is done very nicely, and I'm going to take the module, the curve tracer plugin, and I'm going to bring it over and show you what it looks like inside, because it's very pretty. And then we'll plug it into Tech mainframe, and we're going to curve trace some transistors. Okay, I'll see you soon. Right, so here's the curve tracer itself. This is the 7CT1N. It's a 1-unit plugin. We have a vertical sensitivity and a step amplitude. This is the collector drain volts. You've seen it on the schematic. This is just position, and this is the step offset that I was telling you about. You pull it to enable it, you push it to disable it, and this is to aid or oppose the step generator. So it actually contributes positively or negatively against the step generator. This is that BNC that I was telling you about. You're meant to take this out from the unit and plug it into a nearby vertical on the front of the oscilloscope. And these are the main connections to the device under test. There's another thing that I forgot to show you on the schematic. So first of all, this is the potentiometer that sets the collector voltage. And in order to warn you about high voltage, when this point exceeds a certain step, a certain point, also in accordance with the position of these two switches, there might be dangerous voltages present on the terminals. In order to warn you about that, there's a simple, basically just an LED flasher that gets enabled by a level of voltage higher than something here, actually lower, because it measures it on the negative edge of the signal, but you get the point. When the voltage here is above a certain threshold for a specific time, it means that there is a dangerous voltage here that might harm or injure somebody, and it might also be present on the collector terminal. So this thing starts flashing. What I really love about these tech plugins is that they're very easy to take apart. You just, and you're in. So this is the entire device. Again, it's very, very nice. You can see that I've been here before and I've recapped the circuit. There's a few capacitors that I replaced. This one as well. This one's the 0.1 microfarad in the oscillator. You've seen it on the schematic. And I've changed some other parts around here. This thing, after 40 years of service, needed some TLC, and yeah, this is the transformer. This is responsible for generating the collector voltage. This is the bridge rectifier for it. And these are the cam switches that, when actuated, change the various settings. And you can see some of them are also push switches. So this is one of the push switches. This is another one, and they're all very nice mechanical switches. They're very satisfying to use, and overall just a beautiful, beautiful design. You can tell this is a product of the 70s because of the nice wavy traces. I think you all know how these were made. They were made on transparency sheets with a certain adhesive tape that they would route. So you'd put your component overlays first, and then you'd mark the pad locations, and then using that transfer thing, the tape, you'd route the connections. And that's how circuits were made before the times of CAD, computer-aided design. There's quite a surprising amount of nothing inside, so the device is relatively empty. It's one of the simplest devices from the 7000 series plugins, I think, with the exception of that prototyping amplifier that they had. But it does its job, and it's really, really nice. The backside is even less interesting. There's just a connection to some of the switches and another capacitor. And this is that BNC. You can see it's strain relieved here on the board. So, oh, by the way, this is a repair I made. This collector volt potentiometer is the most used one on the device. It was very worn out. It was basically falling apart, and I couldn't find a perfect replacement. This one has a switch on it that isn't used, and it was too long, so it's shorting out something on the board. So I just stuck a piece of dielectric tape in between them. So I'm still waiting for a proper replacement for this one. Okay, so I'm gonna take you to the tech scope. I'm gonna stick this in and we can measure some transistors or stuff like that. Okay, so as you can see, the curve tracer is plugged into a horizontal slot in this mainframe. This is a 7834, and you can't really see it, but the cable is going from the output, so that BNC I was showing you is going from the output to one of the inputs of this vertical. This is a 7A26. It's a 200 megahertz plugin, but that's completely irrelevant. So adjusting this gives you a different number of steps, and let me see if I can stop it from flickering. This is the storage version of the oscilloscope, and you can see that it looks very nice and steady now with the storage. You can still see the flicker of the storage itself, so I don't know which one is more troublesome, bothering to you guys. Let's go back to storage mode. You can see there's no artifacts on the display when switching between the characteristic curves. That's very important. And you can also do some basic math on this, so like figure out the gain of the transistor, knowing the current per division, vertical, and the step amplitude, etc., and stuff like that. What you can also do, because this thing has two time bases, is you can trigger, you can show the basically the waveform of the collector voltage. If I can figure out how to do that. I remember I was able to do that. Right vertical, alternate, and position, and trigger. Let's see if I can get it to behave. So the trigger source, channel 2. Wait a second. I'll pause and get back when I have it figured out. Okay, so that looks better. It's a bit blown out due to the persistence. If I turn it up, it's not much better, but I can turn this down to make it a little less blown out. So what you can see here is every one of these is one of those triangles that correspond to one of the characteristic curves that we're tracing up top. This is just the vertical, so the collector sweep, and if I turn it the other way around, first of all, the characteristics are inverted, but if I hide this and move this a bit further up, which is this position knob, these are actually the transistor collector sweeps. So this is what the triangle looks like. And if you look closely enough, you can see also the 4 characteristics that we were seeing on the screen earlier. So if I put it back into just the regular and look for it, you can see the characteristic of the transistor back. Let me go dig for a tunnel diode, and I'll be right back. Right, so I have one of these Tektronix tunnel diodes. You can barely see it there. It's beautiful, and you can see the typical characteristic curve of a tunnel diode. And one of the major disadvantages of this device here, so there is no easy way of adjusting the horizontal. So the horizontal is basically voltage, and you have 4 settings. So you have either 5 volts, 2 volts, 5 volts, 10 volts, 50 volts, or something like that. Not very useful. So if you want to look at a device with a very low voltage trip or characteristic like a tunnel diode, there's no really easy way of doing that. Another thing, because this is a storage scope, you can basically see in here, if I could get it to expose correctly, there's a nightmare going on. So this diode has an infinite number of characteristics in between these 2 regions, basically. The characteristic between these 2 points is not very defined, not defined at all. If I would put it on this beast here, which is the subject of another video, you'd see exactly the same thing, but in more detail, because the sensitivity for the horizontal and vertical can be adjusted for that one. The other thing that you can change, as I said, is the current sensitivity per vertical, per division, and that's about it. So this has been the 7CT1N and the Tektronix mainframe. I hope you guys liked it, and see you next time. Bye.